session, we will be seeing the MPPT, different MPPT techniques. Before that, I just had some, like I have to finish a little, so I'll finish that. Okay, by the time the others will also come and join, so that time we will start with the MPPT techniques. Okay, so by that time I'll just finish it. I just wanted to show you that regenerative. So morning I was telling you I didn't bring that thyristor, so now I've brought it. So I'll just show you this regenerative. So let the other participants also join, then we will start that. So here we were telling about the different triggering techniques. So the forward voltage triggering, dV by dt triggering, temperature triggering, light triggering, and gate triggering. So as I already told you, the gate triggering is a common method which is used. And nowadays, if you see digital triggering, okay, before you had a R type triggering, RC triggering with 555 timer and UJT, many different types of triggering were available, like with analog circuits. But nowadays we go for digital because digital has its own advantages. Okay, they are very fast. You have more reliability, and once a circuit is made and you want to change it, you can go for digital. Digital only the programming has to be changed with a little change in circuit. So many advantages are there for such triggering circuits. Okay, so nowadays, as I already told you, digital firing is done. So gate triggering, if you see, you have, these are some of the conventional methods. Nowadays, it's not much used. Still, I just want to give you an insight, like they have R firing, RC firing, UJT with pulse transformers. The pulse transformer is not an actual firing technique, that is for isolation purpose. Nowadays, with digital, you have optocouplers. So before you used to use pulse transformers, and nowadays also you can use pulse transformer for this purpose. So here you can see a simple R and an RC triggering circuit. So in this circuit, mainly when you see here, there is a variable resistor. So this resistance value you go on varying in order to achieve the triggering voltage here. So whenever the required voltage for firing the SCR is reached here, the SCR will get fired. Okay, so one main thing what you have to see in this case is when thyristor is fired and this resistance is somewhat in short condition, then there may be a short. So mostly what we do is whenever they choose this variable resistance value, with addition to that, they usually have a constant resistance here. Okay, in case if this resistance become zero also, short also, there will be some resistance in the circuit. So usually in RC circuit, that will be kept in mind. And similarly, R circuit, in RC circuit, the RC circuit is also shown here. Here you will be varying this resistance and you will be making a voltage which is required firing voltage across this capacitor, and you will be firing it. So you can just see some of these circuits are already there in many books. And you have UJT type of triggering. In UJT triggering, this is the UJT like construction wise, this is the circuit given here. And internally it has two resistance with a diode structure like this. It has RB1 and RB2. So the intrinsic stance of ratio, eta is nothing but RB1 divided by RB1 plus RB2. So this is the eta value. And this is the characteristics of a UJT, and this negative resistance region, the region which you can see here, this negative resistance region is mainly used for acquiring the pulses. Okay. So here UJT triggering relaxation oscillator, if you see here, in this circuit, this is the negative resistance region. So during this negative resistance region, across this B1 and ground, if you take, you can get a pulse here like this. Okay, similarly, this drop, you can again get a pulse. Now our requirement is what should be the frequency of this pulse, at what frequency this pulse should be repeated, and what is the pulse width. So both of the things, the pulse width can be adjusted by changing the RC value. That is the time constant there. So if your drop is a bigger drop, automatically your pulse width also will be bigger. Okay, so that this slope can be adjusted by the RC constant. See this R and C value, when you adjust this, automatically the slope can be adjusted. And the other thing is, when this pulse has to be repeated, that you can get by the frequency which is given here. F is equal to 1 divided by RC ln 1 divided by 1 minus eta, where eta value can vary from 0.68 to 0.82. So this is the variation you can have. And where F is equal to 1 divided by RC, where RC is the time constant. So you can fix it according to our requirement. So this is how you get the UJT triggering like a circuit. Next, a pulse transformer in the firing circuit, that is mainly for isolation purpose. you know, like power electronics is a very, in power electronics, whenever you're doing the hardware, the very important thing is there should be isolation between the power circuit and the control circuit. So the control circuit is a circuit with which we are going to fire some thyristor or something. That is the control circuit. It may have a controller like microcontroller or FPGA base, so any type of controller it will have. Then you have some optocoupling, because once it comes out, there should be some coupling, because the other one is the power circuit at very high power level. And then you have a driver, because those thyristors are at higher rating, and these voltage which is coming out from the controller is very less, maybe 5 volts maximum. So max, or some 12 volts. So sometimes the thyristor may require 24 volts, or sometimes even 9 volts or 12 volts. In that case, you have to drive that voltage. For that, you use driver ICs. Okay, so the pulse transformer is just used for isolation purpose. And here track firing circuit is also shown. Mainly I just wanted to show you this gate trigger, like the isolation circuit here. So this is the isolation circuit, like here it is the optocoupler based isolation. So that is what I wanted to show you here. This is the thing. And these are now some of the firing circuits. You have different types of firing devices, that the devices that can be used for producing the pulse here. So you can see a PUT, programmable unijunction transistor, SUS, silicon unilateral switch, SCS, silicon control switch. Okay, and then you have the like, yeah, these are the different like you from UJT it started, UJT, PUT, SUS and SCS. So these are some of the devices that are used for firing purpose. Similarly, you have the SBS. You can see here SBS, that is silicon bilateral switch, and you have the STS, silicon trigger switch. DIAC is there. STS, that is asymmetrical AC trigger switch. These are some of the switches which are used. Okay, these are not the switches, actually these are the firing circuits which you can use for firing a thyristor. So next is the protection of a thyristor. That is also very important. So you have the snubber circuit, over voltage, over current protection, and the gate protection. So these are the different protection circuit. So first, like heat sink. So heat sink is a very important device which is used for protection of a thyristor. So you have proper design also. So there are a lot of design parameters. You can just go through the machine design books or many of the websites. If you go, their design parameters are also there. So the heat which is generated has to be dissipated. So here you have the fin type heat sink or hockey puck type, and you have assembly of power converters. So the power converters, you should see a converter around 3-phase, 6 thyristors will be there together. So for that also, as a whole module this heat sink comes. Then you have the stud type as SCR. So there are different types of heat sinks available here. Okay, next is the snubber circuit. So this is the circuit which is used for dV by dt protection. So this portion, this is the main portion which is used for dV by dt protection, and this inductor is used for di by dt protection. That is the rate of change of current. This will di by dt, that is the rate of change of current, will be protected by this inductor, and here dV by dt is protected by this snubber circuit. Okay, so this is the snubber circuit. So now next we will just see the working of this. Initially, the thyristor, when you turn on the voltage, the DC voltage across this thyristor, what will happen? Suddenly the voltage will increase. So there is a dV by dt, there is sudden change in voltage. So the device may get damaged. So initially what we have a capacitor parallel to this thyristor. So when you put a capacitor here, initially the voltage will be across, when a DC is turned on, the voltage across this capacitor will be 0. The sense it just acts like a short here. Okay, so when there is a short circuit, the voltage will be 0. After that, what will happen? The capacitor will start charging. Okay, so initial stage here will be say plus, minus. Like charges are there on the both the plates, like plus and minus, like this. Okay, so that time the voltage is across that is 0, plus minus, it is like this. Now once it's at that time it is like a short when you're turning it on. After that what happens? It goes on charging, and at one instant At one instant, what will happen is you will have all these plates minus and all these plates plus at the final instant. In the sense, first it was short 0 volt. After that, the charge started developing there, like it started charging, and at one instant, the final instant, it will get the same voltage here, Vs. The source voltage will come across this capacitor. In the sense, the voltage across the thyristor is slowly developing from 0, 10, 15, and at last, if the Vs value is 230 volts, 230 will come across the thyristor. So here, the across the thyristor, if you see, slowly the voltage is developing, and once it has the full voltage, now the thyristor is ready to get triggered. Okay, so now you give an external pulse to it, automatically the thyristor will go into conduction. So now what happens, once it goes into conduction, this is short here. This is working, it is short. So what will happen, this will start discharging through this thyristor. So what will happen, already the source current is also flowing, with that the IC capacitor current is also flowing. Sum of these two, what it will happen, it will be a larger current and that will damage your thyristor. In order to avoid that, you have put here a resistor. You can see here a resistor which is connected, that initially it is not required for protection, but when the thyristor is turned on, that may damage a thyristor, the current through the capacitor as well as the source current. So for that protection only, we have put the resistance here. Okay. Next is crowbar protection. So crowbar protection, in order to protect the whole power converter here, this whole power converter, what we do is we put a thyristor parallel to it like this, and when the large current flows through it, what will happen? The current sensing resistor is here. When large current flows, automatically this gate triggering circuit will get triggered, and automatically this SCR is triggered, and this, if it is triggered, it's just like a short, so current is bypassed this like this. Okay, so as such, the power converter can be protected. So this is the crowbar protection. And next, gate protection is there. Gate protection, you have the circuit breakers, fast acting current fuses are there, like fast acting current limiting fuse. Then DI by DT protection, you can have the inductor. For snubber circuit is this. The heat sink is also there. So with that, gate protection is, this is a gate protection circuit. In order to limit the large current, and R2 circuit, R2 resistance is put. In order to limit the voltage, a Zener diode is here which will clamp the voltage, and this R1 and C1 is the low pass filter. So in case like for high noises, this will just eliminate the noise. And apart from that, this gate terminal is also twisted. Okay, so twisting is there, the coils are twisted so that electromagnetic interference or other noises can be eliminated. Apart from the low pass filter, the coil at the gate is also twisted. So these are some of the things. I'm just rushing because I have to start with the next within small time. So commutation I'll finish, and this we will go at. So different commutation techniques. So commutation, as I already told you, it's a process of turning off the thyristor. So you have natural commutation and you have forced commutation. Natural commutation, when it is an AC supply, automatically when the supply crosses the zero. So I can just show you here. So in this way, you can see here, when the AC supply crosses the zero crossing, automatically the thyristor gets turned off. Okay, so at this point you can see thyristor will get turned off, and again at this time when it becomes positive, it becomes forward bias, and when you give a triggering pulse, automatically it will get turned on. So this is natural commutation, and this can this we can do it in rectifiers, because AC supply, then cycloconverters or AC voltage controllers. But in cycloconverter, step up cycloconverter, again you require force commutation. Step down, no problem, because zero crossing is there, but in step up you require a you require force commutation. Okay, so next is force commutation. That is force commutation is by using some inductor or capacitor, you charge it and you just give a reverse voltage across the thyristor, automatically it will get turned off. So self-commutated, Lord commutated, resonance pulse, complementary commutation, impulse, external pulse, these are the different methods. So mainly force commutation is used in circuits where DC is the input, like choppers and inverters. Okay, so like this is the load commutation. In the sense, the load forms a resonating circuit. So when it is a resonating circuit, automatically the supply, like when the voltage like across it resonates like this, automatically it crosses the zero. So there is a current. When it crosses the zero, automatically the circuit is commutated. So these are some of the commutation circuits. Okay, and we have resonant pulse commutation, resonance pulse. Do you require this, or can I skip it and go? Like, this is simple things. Okay, so here also say this is just conducting. When you want to turn off this thyristor, you will be turning on this thyristor. When you turn on this thyristor, what will happen? This will form as a resonating circuit. This capacitor will start discharging and start charging in the opposite direction. Okay, so this will start discharging and start charging in the opposite direction. So here becomes plus, here becomes minus. So at this time, here plus comes and minus comes, and this will get commutated. Now what will happen? This capacitor will start discharging in this way, and as a current pulse, this will try to oppose the current coming from the thyristor. So the thyristor current will go on decreasing, and one instant it will get turned off. Okay, so these are the different methods. Or what you can do in voltage commutation circuit. I'll just show you the voltage commutation circuit. In voltage commutation circuit, what you do? In voltage commutation circuit, same way. Here, this has to be initially charged like this, and when you want, the current will be flowing through the main circuit. And when you want to turn off this T1 circuit, you will just turn on this thyristor T2. So when this thyristor T2 is turned on, what will happen? Here, yeah, initially this is like this, this thyristor is turned on. This will start discharging. Sorry, the like initially what happens is, when they say, let us consider the initial condition first what happens, this thyristor is on and it current will be flowing like this. At the same time, at the initial condition, with this thyristor current, there is a capacitor current also flowing through it. Okay, because initially, yeah, already it is charged. So what will happen? The capacitor current will be flowing like this. This will form a resonating circuit, and capacitor current is flowing through like this. So what will happen? Capacitor at this instant will be, this will be positive, this will be negative, and it will be reversely charged. Now it is reversely charged, and that circuit is open. Now at any instant you want to turn off this thyristor, what you do? You will be turning on this thyristor T2, the green one. That now what happens? This plus comes here. You're giving a reverse voltage across this thyristor T1. So this capacitor voltage will come across this thyristor, and thyristor will get turned off. So this is giving a reverse voltage commutation. Okay. So these are the different types, methods by which you can turn off the thyristor. So just imagine there is a single thyristor, but how many circuits are involved in it? You have a voltage circuit, commutation circuit, you have firing circuit, you have supply circuit, power circuit. So all these things are involved. Still, we just take, it is only a switch there. Okay. So with this, I am just closing this thing, and let us go to the afternoon session. And before that, I was just telling you about the regenerative braking. Sorry, it's not regenerative, regeneration process. The thyristor, once it is triggered, it continues. So just for that, let me show you thyristor. Let me show you a thyristor. Okay, so I think all of you can see a thyristor here. I'm having it in hand. Okay, and this thyristor is having 3 legs. Okay, can you just enlarge it? So here the center one is the anode. Towards my right, which one I'm touching is the cathode, and one is the gate. So if she enlarges it, you can see it clearly. I'll just show you the process of regeneration. That is regeneration. Any thyristors you can take of this type. So I'm just showing you a thyristor. Okay, so there are 3 legs. In the center leg is the anode. I think all of you can see the center leg, that is the anode. The body is also anode. So if I want to connect anode, instead of in the center, I can even connect it at the top. So that is what I have, a battery with me. Okay, battery with an LED. So here the positive and negative I have taken, and that anode, you can just have it like, okay. Okay, so this is the circuit. Okay, so anode I have connected at the top, and towards my left I have the gate circuit, and towards my right I have my cathode. Okay, so now this green one is the cathode, like negative terminal. Positive is this white. So white I have already connected. So this green I am connecting it to my left side. Okay, I've made my thyristor forward bias. Is it? I have made it forward bias. Now what I have to do, this right end terminal is my gate. I have to give gate pulse to it. Once I give the gate pulse, this will turn on. Even if I remove the gate pulse, it has to conduct. So now, in order to give a gate pulse, I'm just taking a screwdriver. I'm just going to short my anode and gate. So little current will go and then I'll remove it. So in order to short it, I'm just connecting these two. So you can see my LED is glowing. Okay, I've connected. Now I'm giving gate pulse to it. Now I'm removing by gate pulse. It's not properly connected, otherwise it will be latched. Oh, sorry, I just connected. When I turned it went wrong. My cathode is towards my left here. That's what I'm saying. Otherwise, it has to latch. So here now it is correct. When I am seeing, so now according to you, the right side is a cathode. Okay, so center one is anode. This one is a gate. So now I'm just giving the gate pulse. Okay, so now it is glowing. Now I'm removing my gate pulse. Still it is in conduction. You can see here. Okay, so now you gave a gate pulse to it and now it has gone into regeneration. Now it is continuously until this battery is fully drained, it will go in conduction. You need know that is here you require, when you want to turn it off, you require commutation. How will you do it? Remove the supply automatically. So DC, no problem. Supply is not there, automatically turned off. Or if it is AC or something like say if it is say in DC also, when you want to forcefully do it, you can give a reverse. Like if you have a capacitor or inductor, reverse voltage across this can also be given. So if I remove this cathode, automatically this will get turned off. So this is a very simple thing. So now you understood. It's not a tough thing also. Okay, you can. One thing, some people will be afraid. Power electronics itself is a big thing inside their mind. They think power electronics is a big subject. It's nothing like that. Once you start doing work on it, it will be a very simple thing. Okay. So now we will go into the others, like next one, MPPT. So now we will just see the converters for MPPT and its hardware implementation. This is a topic which we are going to see, like how to implement MPPT. What is MPPT? Maximum power point tracking. So, okay, we are just going to see how to track maximum power from a solar panel. Okay, so we'll be just seeing different methods. If you are more interested, I can just give you even artificial intelligence and all those things in these coming classes. Now I'm just going to tell you the basic methods. Okay, if you are really interested and if you want more lectures, we can have more lectures, because I thought fully putting in MPPT and all these things also will not be good. So I'll try my best. How much I can cover, I'll cover. So first of all, the global solar potential, if you see, this is the thing, around 80% of the whole world has solar potential. And India, you can see it is coming in the orange region, where in India also you have good solar potential. And the main problem what we face today, you all know, it is scarcity of energy and quality of power. Many other problems also, pollution, but major, like being electrical or electronics engineers, the problem what we face is, one is the scarcity of power and another one is the quality of power. Okay, so scarcity of power, how will we overcome? The only thing is go to renewable energy. And now in India, if you see, you have good wind potential also and solar potential. But in wind, if you see, there are a number of disadvantages, but it requires a very large area. And if it is a large area, the people, like all the like what telephone, like all not telephone, like say wireless communication, all those things also will be affected by this wind. And other thing is, there will be a humming sound always, and wind is also not uniform. So there are problems, but there are some places like in say Tamil Nadu, Rajasthan and all, it is going in good strength. So I don't say wind is not good. Wind is also good for India. It has a good potential. Still, if you see solar, Solar has number of advantage. It doesn't have advantage. Like one thing is, say nowadays a rooftop. Many of the places above the house, you just, that space is just wasted. You just have solar panels. It will give you the supply. So many advantages are there for solar, and only main disadvantage of solar. What is the main disadvantage? Any idea? What is the main disadvantage of solar? Yeah, dependability. But say I said like India, it's having a good potential. Around 90% you get potential. I'm saying night hours. So for that you can go for storage. That is one thing. That say like wind also you can't. You don't have any guarantee that you will get it always. Okay. So that is also there. But anyway, what is the main disadvantage? Space and cost. Compared to the, say, anyway we have to go for renewable energy. Even go for wind also it requires a large area. Cost is also good. शेडिंग, ओके, शेडिंग के लिए भी बहुत सारा रिसर्च है, शेडिंग भी ओवरकम कर सकते हैं. स्टिल मेन डिसएडवांटेज. इसमें हम कुछ डिस्ट्रॉय नहीं कर रहे हैं. हमारे रूफ टॉप में डाल देना. यू जस्ट पुट इट ऑन योर रूफ टॉप. यू आर नॉट गोइंग टू डिस्ट्रॉय एनीथिंग. Life, yeah, around 20-25 years, it is there. Like it is having at least in that sense. If you see, nowadays the concept is DC itself. People say DC is good, and in foreign countries, concept is DC houses. They have started with DC house. They say, why do you want to again convert to AC and then DC and all these conversion power electronics device also you remove, only you have a charge controller, that is a DC to DC converter. That is DC house is the concept everywhere, and in India also HVDC transmission we are going into, because before the problem was you have to like say when you want to transmit for a long time you have to step up or step break. Step up is required, and again at the other end you have to step down. Otherwise, what will happen? You have large losses. So that's why we went for AC, because at that time we didn't have any stepping up or stepping down until this power electronics is not until power electronics came. Before, what we do, we have transformers. You step it up and you just transmit for a long distance. Their losses are less. Okay. Yeah, that is what I wanted to come. The efficiency of the solar cell is very less. Can you tell me what is the maximum efficiency till now? What they have achieved in a solar panel, solar cell? 25%. Any other idea? 25 is not correct. Huh? Less than 10. That is also not correct.
Less than 16.
Less than 16. I got an answer from the center. I'm very happy, but that is also wrong. It's not less than 16. Any other idea? Say, what you told is to some extent current, less than 16, or some people here at center.
18.
Huh?
18.
18, no, 18, 16, all these things are wrong, but still I can accept it, because in India or in our labs, what we have is, it is 12 to 13%.
12 to 16.
Like 16% also you can say, that is also correct. But I am asking, what is in research, what is the maximum efficiency achieved according to NREL, National Renewable Energy Laboratory in US?
26.
It is not 26 also, it is 46. Okay, so it is, they have achieved till 46. You can see the data here. I'm just enlarging and showing you. Okay, so this 46% is achieved using multi-layered thing, multi-junction cells. So you can see here, multi-junction 2-terminal monolithic wafers are used for achieving efficiency of 46%. Okay, this was the data of 2015-16. It is around 16. Around 16 since last year. They have achieved till this using multi-junction cells, 46%. Okay, I think you can see here the 46% here. This is using multi-junction thing. You say the same thing using thin film technology. Even now, the thin film technology has also come. Solar panels, how much thin you can have, that is also having, because in cars nowadays you have the thing of hybrid vehicles. Nowadays thing high. So nowadays they have the car with their solar panels at the top. So you can generate your own like energy, and you can give it to the grid. That is the future. In future, if you see the car, what you're putting in the sun here, it will start generating money for you. Whenever you go to the office, you have a solar topped car. You put it in the sun there. That time now we go and search for shade. At that time you can put it in the sun itself, and you have this power trading. They will be just, you will get some message. Now it's the peak hours, and you, if you are willing to sell power, please get it. So what we do, we just go and set okay and go and plug in your car to the grid. You have nowadays you have the charging stations and plug-in stations. You go and plug in, it will start discharging your battery. Okay, now message will be coming, your battery is discharged 30% and it is charging to 40%, 50%. And if you feel, okay, if I want to go home, I require some 30% in my battery, you can just disconnect it with your mobile app. Nowadays, all apps will be, in foreign countries, they are doing all these things. In India also, this is coming. So here, in future, I think all of you will be there behind, like my car also earn money for us. Okay, so this is the future. So in that case, you require thin film technology, thin film solar panel. Otherwise, the solar panel is so heavy and you're having it over the car, then how your car will drive? Okay, so those things, nowadays thin film technologies have come. In thin film, if you see, you can see the data. In thin film, there, this is the green one, 23.3%. So you can see here, thin film, what are the concentrators, different CIGS, and CDTE. So these are the different materials used, and accordingly 23.3% is the thin film technology we have achieved. And the normal technologies like the emerging PV technologies, other technologies, it is 20.1% we have achieved. But in India or in our labs, we have, that is only 13%. We have done the experimentation here. We get 13 or 16. The data what you're telling is might also be correct. There are panels with little less efficiency. So still here, this 46% is also not a big thing. If you can achieve you can develop a solar panel with 90% efficiency, I think you can get a Nobel Prize also. Is it? Because that is the future. People will surely accept this. So you can just, you can have a lot of research in this area. Mm. Mm. Now, when it is running, you don't connect. What is the need? This is like, say, when car is running also, your battery will get charged. Okay, it is in moving condition, but not like when it is moving also, you can track. Some light should fall on it, that's all. It is not necessary that it should be stationary. No, no, you are not supplying it to the outer world. You can charge your own battery. Your car battery you can charge. But the concept is, when your car is simply there standing, it has to give power to the thing, so that it can earn money. Even nowadays, if you see in houses, many people, they are installing it in their houses, and they are using all the power. And during daytime, daytime they are utilizing it, and during nighttime they are storing the battery, and they are using it during night. So when it is surplus, what they do, they can even give it to the grid. So in many places in India also this concept have come, but actually the smart grid concept fully has not been established. It is in the initial stages only. So when government takes up this, then many people will get interested and they will start selling their power. Yeah, around 10 years, I think mostly within 10 years, we will be moving towards this. Yeah. Now it is for they are doing a number of experiments. Even our students have done where they have a bulb far. You have the induction principle only, and that is now the wireless chargers have also come. Okay, but high power transmission they have not. They have done to some extent, like some distance wirelessly. They are transmitting, not long. So you have some Google videos. You can just YouTube videos are there where power can be transmitted wirelessly also. That is also possible. So DC power, now DC wireless chargers have come. The mobile chargers, wireless chargers have come where the DC is being transmitted wirelessly. Okay. So next, the cost wise also, if you see PV, like say compared to the wind offshore, the PV is very less. So this is in euro, the amount is in euro. So you just take like say 1 euro is around 100 rupees, like simply like that. If you take, you can see here PV utility, it is around 14 point something rupees per kilowatt. And PV utility, it is around some 11 rupees per kilowatt. And wind onshore, it is around 9 per, like say not 10 point something. Offshore is around 18. Okay, so not 18, more than 19. I think 19, I can say 19 point something. And biogas is very costly. And all the other coal and natural CCGT, that is natural gas. All these things are less, but they are they get exhausted. So we are not concentrating on them. So here solar, if you see as an utility, like a larger scale, the cost is comparatively less. Wind is also less, but compared to wind, PV has more advantages, we can say. Okay. So now coming to the maximum power point tracking. So what are the different methods by which you can track? One is by automatic sun tracking. This method is nothing but the mechanical tracking method. How will you do this? So you have a solar panel. Okay. Motors. So you will have some light sensors there. Okay. And according to the sunlight, you can just, angular movement of these solar panels can be done, and it will move from east to west, and automatically the maximum power can be tracked. So is that good method?
अभी तक मैम only two quadratic axes ही available है, fourth नहीं available.
नहीं, 4 भी लोगों ने किया है. What they say is like year, the whole year, if you see based on the sun's position, there is a small shift also. So they are saying it is only this one 0 to 180 degrees, one single direction is not so. So they have this concept of four direction, that it just tracks the 4 direction. And one of our student who is going to do this project, all the 4 direction, he will be showing you the real time project on the last day. Okay, so he has done this full tracking.
कोशिश करता हूँ कि my students work on this maximum power tracking based on 4 directions.
Okay,
अभी तो 2 ही आ रही है.
4 directions our students have done, and that is been kept in this course. So you will be seeing the 4 direction also. Okay, four quadrant operation, like all the 4 direction movement can also is also possible, and that will be shown to you. So this automatic sun tracker, one of the problem is the power which is generated, again you have to give it to the motor, and the motor is wasted there in the motor. Okay, so now that is a mechanical type of tracking system. Now the electrical people have come out with a tracking that is said to be the electrical tracking method. So what they say is, instead of just moving this panel throughout, let us see the latitude and longitude of the state in which you remain, or the place where you remain, the city where you remain, and fix the panel in that particular position. Okay, in one particular position throughout the year, might be it is giving a better thing. You analyze that and you fix it. And in internet now it is available. For the Chandigarh, this latitude and longitude, this is the angle at which you have to keep. So it is already available. So go and fix it in that position automatically. In that position also it will not track. Now you can have electrical tracking method. Okay, in electrical, you know that when will maximum power transfer from source to load? Whenever the source impedance and the load impedance matches, okay, whenever the source impedance get matched with the load impedance, you say maximum power will transfer. So the same logic can be used here, that is electrical tracking method. So there are different methods for tracking this electrically. So some of the methods are given here. One is the perturb and observe method, incremental conductance method, artificial intelligence method, you have optimization method, GA, PSO, so many methods are there. So which method to use when? That is the next thing. When will I go for GA? When will I go for artificial intelligence? When will I go for perturb and absorb? That is the confusion now, is it? So next we will see that step by step. So first of all, we see this automatic tracking system. So here you can see a solar panel is there, and as the sun position changes, this also changes. So this is the automatic tracking system which we have. Next method as the electrical method which I told. What we have to do? We have to do maximum power transfer. In the sense, source impedance and load impedance should match. When will it match? Where at this peak point. Say if this is the PV, and now leave the PV characteristics. We'll go next. Let us take a simple example. Okay, we want to find the maximum of a curve. There is a curve, and I want to find which is the maximum point. When will I get the maximum point? Say for example, the height of a projectile is here. I am just throwing a stone up. So it will take a projectile like shape like this. I want to find when did it reach the maximum. So here the projectile equation is given here. You can see here d of t is equal to vt minus half gt squared. So when you want to find the maximum point, according to calculus method we use, what we do, we find the slope. Okay, when the slope is 0, we say we have reached the maximum or minimum also. Whenever there is a steep point also, when you reach the minimum according to calculus, when the slope is 0. What is slope? dv. See here dy is given. So dy by dt is the slope. So here in this case also what you have to do, this is the dy equation, that is the projectile equation. Just find the differential, partial differentiation of this dy by dt, and when this value is equal to 0, you say you have reached the maximum point. Same technique only you use in your perturb and observe method. There also I'll be just telling you that method. So that is a calculus method. You are finding the slope. Okay. So here, how will you find? Say when the slope is 0, you understood that you have reached a maximum. But how will you understand that whether you have reached a maximum or a minimum? Because when the slope is 0, you would have sometimes reached the minimum also. Yeah. So next you have to do the second differentiation. When you do the second differentiation, when you get a negative, see here you have seen when you do the second differentiation and you get a negative value there, you find that you have reached a maximum point. So this is the thing. Second derivative demonstrate the derivative is a maximum. That is, for a maximum, the second derivative is negative. When the second dy by dt is less than 0, when it is a negative value, you say you have reached the maximum. When will you reach the minimum? When you take the second derivative, and if it is a positive value, you say that you have reached a minimum. Okay. And next thing is, if there is a change, okay, there is a change, you want to find whether it's a maximum or minima. In that case, if the second derivative is not equal to 0, you say that there was a change, but there is no maximum or minima. That was only just a inflection. Okay, that's just a change. That is not a real maxima or minima. So this is how you find it using calculus method. In mathematics we use this calculus method. So same method can be used here for this PV also. So PV characteristics I'll show. It is something like this. So in this method also, you just think you have blindfolded a man and you're just allowing him to move in this area. So will he be able to find the maximum? Will he be able to say, I have just closed one person's eye and there is a slope like this and I'm just telling him, leaving him alone. Will he be able to go and reach the peak? He can move and he will reach, is it? By judgment, he will go and reach the peak. He can reach the peak because there is only one peak here. Okay, there is one, he can go and reach. He can say, okay, this is my peak. Now just think, the slope is like this. Will the same blindfolded person, I am just leaving in this room where there are multiple peaks, will he be able to just find which is the peak? He will go to number of peaks, but he will not be able to judge whether I have gone to the maximum. No, he is walking the hill. It is like hills. Okay, it is not like you can touch and tell. I am telling it is a room with lot of hills. He is moving about. He is blindfolded. In that case, it is not difficult. He will not be able to find because there are number of hills which are of equal. See, if you see these two hills, this hill is also almost finding maximum. This is also a maximum here. This is also a maximum. Sometimes when he climbs this, he will feel okay, this is maximum. After that, he is going through some small ones. Again, he climbs this, he will find this. So he will not be able to find which is the maximum. So now comes first single method, only single slope or two slopes. You can go for calculus methods like perturb and observe, incremental. Once there are multiple slopes like this, you will not be able to go and find. For this, you go for algorithms like optimization, that's GA or PSO. Now we understood when will we go. So now what will happen? Now this GA and PSO, what you do, you take a group of population. It may be your chromosomes, or PSO, what you do, it may be a group of birds. And these birds are your solution. And what they do, in iteration by iteration, they move towards your solution. Your solution is a peak there. And this is in this case, this is the peak. Any type of algorithms you can use, any stochastic algorithms you can use, and you can go at. Everyone will find you a maximum or minimum, but each method has its advantages and disadvantages. PSO, it will find you the solution very fast. Okay, than GA. But GA will give you a better result than PSO. So each algorithm has their advantage and disadvantage. So where you're going to use? You're going to use in live, online application. So in online application, the best thing is your algorithm should be faster and give me an accurate result. Then you go for PSO. If the GA is very slow, you go and put it in online, it is very difficult, is it? So this is the way you have to do it. So you can go for optimization algorithms when you want to find this. So in that case, what you do, you just like say in GA also you have different methods, like you're selecting the population, then doing crossover, then you mutate them. So in crossover, what will happen? It will just find the location. Okay, my maximum point is somewhat in this area. It will find, that is, it is exploring it. But mutation, what it does, it exploits. It will go and exploit that. So that's why we say mutation is also required, but it requires a positive mutation. Okay, negative mutation will sometimes go and take some other peaks. So there are a number of things which you have to learn when you do go on doing algorithms. You will understand it here. In order to get the multiple peaks, you go, and those multiple peaks also, say in case of our PV, how it is. That is what we are going to see. So in PV, when this multiple peaks come, when there is some partial shading, when you have partial shading effect, this multiple peak will come. Say you have a string of PVs connected. Mostly these, we, according to a voltage and current rating, not only one module, we'll connect a string of elements. So here what happened, in this case, the first string, there is no partial shading. In this string, there is no partial shading. In the second string, if you see, only one of the PV is shaded. In the third string, like, sorry, the first string here, this is 1, 2, and 3. In the first string, 2 PVs are shaded. Just think there is a tree or something and these are shaded. So what happens to the current? Say the blue one, fully it has grown. In the second, the blue one till here it was okay. After that, this green one is bypassed current. And similarly, so you can have diodes for bypassing so that this effect can be overcome. So here in this case also, say you have this red line. So this can be over, like the current will be bypassed like this. So in this case, you can see when there are 3 strings, this is the blue one, that is full current is flowing through it. The green one, only one PV was shaded, and there are, when 2 was shaded, you got this red. So the equivalent, if you see, you have 3 peaks like this. So in this 3 peaks, this peak is a local peak and this is also a local peak. And this is your global peak. Okay. So in GA also what happens, say you have a number of peaks like this. Okay. So what happens, GA, when you do crossover, sometimes it will go and get locked in the local peaks. It will say my peak has achieved. So that's why you do mutation. In mutation, what you do, you change the place itself and you put it in some other location. So then again, when the algorithm runs, it has a chance of getting the maximum point. So that's why you do mutation, in order to exploit the point, going nearer and exploiting it. So similarly, PSO also, you do the same thing. In PSO, what the bird does, the bird just sees its own position, its neighbor's position, and the whole group, like a whole social parameter, the whole group parameters, and it just changes its position and moves towards the solution. That is the global peak. Okay, so that is the main requirement here. Okay, so next, now how to find this? These peaks, if you see, when you run an algorithm like this, genetic algorithm something, there is a group of solution and there are some 3 peaks. So what it does, it just moves and it just goes to the peak. So here in this case, when you put the peak, it automatically, the algorithm will run, it will find where is the peak and it moves towards the peak. So this is the case of a partial shading which is fixed. Okay, but just now take a partial shading which is not a fixed partial shading. Okay, trees also, the tree shade is also not fixed, but for a little time it is fixed. It takes a long duration according to sun position may change. But there is a cloud. It may suddenly, like more drastically, the position may change. In that case, you can see that the peak is dynamic there. Okay, at each instant the peak is changing. So how our algorithm should be? Our algorithm should be more dynamic there. It should go on choosing which is our peak. It has to go and find which is our peak. So here, the algorithm which you choose should be more dynamic in nature, and your like objective function should also change the like the objective function should be in dynamic objective function, so that you can just go and choose it. So these, I am just giving you idea that if you are doing research, where are the scopes available. So now some of our students are also, we have given some problems to students like that. When the peaks are dynamic, you just find out some algorithms in order to find it. Okay. So there are many algorithms. You have ant colony algorithm, you have bat algorithm. Okay, according bats also, you according to this sonic sound which they are sending, the vibrations, sorry, the signals which are coming back, it is identifying. So there are a number of algorithms in order to find the dynamic peaks. Okay, you can just go through different algorithms in wet, and if you want to take some like if you want to take a problem in this, you can identify problems for your MTech or PhD level. This is very good. Even in when you want to connect a PV to a grid, you can just think of a dynamic changing peak. Like this is also, and there are algorithms where you have probabilistic function. Say the sunlight is not constant, so in your function you can make a probabilistic function there for your uncertainty of PV. Your PV voltage is uncertain there. Okay, so you can introduce probabilistic function. In that, probabilistic neural networks are also there. So neural network will give you a better like optimized answer or intelligent answer. In that, you put a probabilistic function where the sun's light is not uniform. So that connected to a grid. So there are many problems which can be solved using these techniques. Okay. So now coming to our PV. So our PV, if you see here, this is the PV characteristics. You have the power as well as the voltage, and this is green curve is the voltage versus current. Okay. So now what is our aim? This now I'm just going to explain you the method of perturb and absorb. That is a conventional method. Okay. So if you understand that, then step by step how it is operated and how can you improve your method, you can just have it. So in this method, if you see, first of all, at any instant, say now at 3 o'clock or something, I'm just going and measuring my voltage and current. So let my voltage and current at this instant, let me say that my voltage was V1 and my current was I1. My voltage and current are these two values. Okay. Now again what I do, after some time, I just perturb the system, I just disturb the system, and I find a new point. So my voltage and current was here, new one. This V2 and I2 are my new voltage and current. So first case my power was P1 and the second case my power was P2. So in this algorithm what you do, you see the change in power. Whether the change in power is a positive change or a negative change. So in this case the power is increasing. So there is a positive. So if you do P2 minus P1, higher value minus P1, it is a positive change there. So if there is a positive change, you can see that I have not reached my maximum. There is still chance to go up. Okay, that is how you find go. Again, you continue this, and one instant you will reach this peak. Once you reach the peak, again you disturb the system, it may go down. So when it goes down, what happens? The power is there decreasing because this is the power. So in this case, the power was, say if it is P3 and this power is P4. Here, if you do P3 minus P4, you will get a negative value. Is it? Sorry, here. So P4 minus P3, that is the later one is P4. So P4 minus P3, if you do, it's a negative value. So you understood that you have crossed the power. So again, go to P3 itself. Again, you go to P3. So P3 minus P3, when this slope is 0, you get the maximum power. So that is the algorithm which you have to implement in order to find the maximum power. So I am telling you every time you are measuring it and you are disturbing the system. What do you mean by disturb? How will you disturb the system? How will you disturb the PV? I didn't get this question from you. You should ask me. Is it? You are likely to ask. Okay. So that is a very important thing. Is that I am telling my PV is there. I measuring. Okay, you can understand. You will have a voltage sensor, current sensor, and you measure it. You have some Hall effect sensors or potential dividers, something, and just measure it. Okay. But how will I disturb my system and change the? How will I get a net? So that I'll just show you. So this I have to explain first, and then I should have gone there. So this is the MPPT system here, and here in this we did this experimentation in our lab. So the participants here, I can take you to the lab when some session is a little free. I'll just take you. So here, if you see, this is a PV. Okay, this is the DC to DC converter. So I told you about the DC to DC converter. That is a charge controller. So that is that, and this is our load. Okay, here we are just having a resistive simple load. Okay, the same thing. The next class, tomorrow I'll show you this whole system. I'll just connect to an inverter, multi-level inverter. So my inverter's output will be my load at that time. Now for this experimentation, simply I'm just considering here as a resistive load. This is just a resistive load. So now what I'm doing, I am just having a potential divider here. Okay, so first of all, when we started Hall effect sensor buying, it was a very tough job for here. Here, one full year process will be going on. If we want to get a component or something, then we have to make budget, that, this, it goes to the B. So it was a very tough thing. So what we made our own sensor. It was nothing but 2 resistors. We made it pot. So it was a variable pot here and one more resistor here. That is also a variable. And 3 resistors we put. One constant resistance also we put here. Okay, that constant resistance, let me show it in blue here. So one constant resistance. Why this constant was put? When I vary both to 0, sometimes there will be a short and that's all again problem. So what I did, one small resistor I put so that circuit is not a short. So now in this thing, what we actually did is, in case say my voltage is 17 volts here, I made some 16 point something drop here and only 1.7 was the voltage drop across this resistor. 1.7 was the drop. And this 1.7 I gave it inside my controller. Because all the what type of controller can be used here? What is the controller there? The controller will give a firing pulse for me. Okay, in order to fire this switch in the DC to DC converter. So this controller may be a microcontroller, it may be a microprocessor, it may be a DSP processor, it may be a FPGA processor. Okay, any type of controller. That gives me some pulse. Because I told you nowadays we go for digital firing. Digital firing also with microcontroller. Tomorrow's class I'll just show you how to generate a firing pulse using a microcontroller. It is a very simple thing. I'll just show you using MATLAB how can we generate the firing pulses. The MATLAB only will show the simulation here also, so you can correlate it. Okay, so here why I'm just making this voltage 1.7 here? Because any controller you take, say this circuit, the one which I'm drawing here in green, I think all of you can see this. This is said to be the power circuit, which is at a high power level. Okay, here it is a small thing. Say in laboratory when we did, it was only a 37 volts PV module used, 37 watts. Okay, it was only 37 watts in the sense open circuit voltage was around open circuit voltage was 21.2 volts and the short circuit current was some 2.1 amps. Okay, and the power was around some 37 watts. The panel was something like this. Okay, it was a small panel there. Okay, and the DC to DC converter, a buck converter we have used, and this is a power, though it's a power circuit, it's a small circuit, but you just think when I want to connect a full PV panel, PV source to the grid. So it will be a very big power level. Okay, so such a power circuit is there, and this control circuit, what is the voltage level of this control circuit? Yeah, it may be say very, yeah, mostly 5 volt and you can go until 24 volts. Okay, आपका maximum 12 volts का भी है, maximum FPGA वाला गया तो you can go up to 24, not more than 24. You just think when a high voltage from the power circuit flow into this, what will happen? It will get damaged. Okay, so you can have optocoupling, you can have all these isolations there. Still at our laboratory, what we did, we thought not to give high voltage. That's why what we did is we dropped a larger voltage at this upper resistor and only a small voltage. So when we do, I'll just show you, we did only 0.17. Okay, for a very safer side, we did 0.17 because even a short or something occurs, our controller will burn out. So we were very careful. We made it only 0.17. If you want, 1.7 is also not a big problem because most of the controllers allow still 20 volts. If you acquire till 20 volts, nothing will happen to the controller. Tomorrow I'll show you the Arduino controller. There they have the requirement, that is they have the range till 20 volts they have given, but still they have said please don't go above 12 volts. In their data sheet itself they have given because they are also not very sure. If you go to 20 and suddenly a short, sometimes their controller may go. So that's why we do what we do, we reduce this voltage to a very low value. So this 1.7 volts, or 1.7 or 0.17 volts take inside the controller, then it will go into your MATLAB environment because in MATLAB only I have written all my algorithms. P&O algorithm or jo bhi algorithm I have written in MATLAB. So when it goes inside MATLAB I will put as gain and I'll multiply it. 10 or 100 से multiply कर लो. So what will happen? Your 1.7 10 से multiply कर लो, you will get 17. So your computer will understand my voltage of the PV is 17 volts. Okay. So similarly, the current also. I have a resistor here in the R3. So this is my current resistor. This resistance value, this current value also I am taking. So most of the controllers, they will not understand the current. So current also in terms of voltage I have to give. So I've kept like this, when 1 amps flow, there is a 1 volt drop. Okay, so that 1 volt I'll take inside my computer and I'll tell the voltage which is coming is nothing but my current. So you have to do calibration there. You have put a pot there and you simply just turn the pot and see what, put a multimeter also and just measure what is the current flowing, accordingly what is the voltage drop, and accordingly you will be giving it inside the controller. Okay, is it clear? So now I told you something about the maximum power like disturbing the system. How will we do that? So here PV is there, DC to DC converter and this. So when the PV is, so now when the PV voltage, this PV voltage, okay, this is, sorry, PV impedance and this load impedance matches, automatically maximum power will flow. How will I match it? I'll just see what is my voltage, what is my current, and then again I'll disturb the system with some duty cycle, and again I'll measure my voltage and current, and I'll see whether the power is increasing or decreasing. So if it is increasing, my say power is increasing, I understood that I have not reached my maximum power, again change the duty cycle. Okay, can you understand? So again and again I will disturb my system with the change in duty cycle. I am just disturbing, when I change the duty cycle, my DC to DC converter will change the voltage there. I am trying to match the impedance and automatically my maximum power will be achieved. So is this clear now how we did it? So now the same example, we can, what is incremental? Now I told you something about perturb and absorb. What is incremental conductance method? In incremental conductance method, what we do is, we just draw the slope. So here, let me just draw this, sorry. Let me draw the slope here. If I draw the slope here, when the slope is a positive slope like this, what does it mean? I am towards the left side of my MPPT point, maximum power point. Let me again draw the slope here. So this slope is a negative slope. So I've crossed my MPPT point. And when my slope is 0, I have reached my MPPT. So that is nothing but your incremental conductance method. So they just find the conductance, current by voltage. You have to just DI by dV you have to do. So that method also, if you see, it's just like P and O only. Okay, that is also a calculus method only. You are just trying to find the peak in different methods. Okay, so this is how the general conventional method of finding the MPPT point. Okay, so next, here this is the buck converter. Okay, so generally the buck converter, the structure you can see here, you have a switch here, you have an inductance, you have a diode here, and this portion, usually in a good books, if you see, they have this LC. So this is nothing but a low pass filter here. Okay, but in many of the books, this capacitor value will not be given. But actual circuit, when you get a real buck converter, you will have these two capacitors. Okay, this is a buck converter. So you, with this itself, say if you want to make this as a boost converter, what you do is anti-clockwise direction, just shift these devices. I used to tell my students to remember, because whenever we ask buck or boost converter, they get confused. Only this inductor will come here, the switch will be here, and this diode in the forward direction like this. If it comes, it becomes a boost converter. Okay, and next is, if you want to just make a buck boost converter, you just interchange these two. So you put an inductor here and make the diode in the reverse direction like this. Okay, just shift both of this, you will get a buck boost converter. Okay, and here I'm not going in depth into the characteristics. Okay, so I'll just tell for buck converter. In buck converter, what happens is, so initially when the switch is closed, okay, when the switch is closed, The voltage across the inductor, if you see, like say if when the switch is closed here, this diode is not operating. Okay, 1 second, I'll just show in the next slide. So you can see here, the diode will be reverse bias, this diode will not be there. Only the inductor, capacitor and the load is there. In the second case, when the switch is open, what will happen? This inductor will have some energy. Okay, so that will be dissipating through this diode. So this circuit, I'll just show you here. So this is the two cases. Okay, one is when switch is closed, you will have a circuit like this. When switch is open, you have a circuit like this. Okay. Now, now these are the equations for LC and inductor and capacitor. Okay, so now any standard book, you just take any standard books, Netmohan also you can take, and Rashid also, they have given for buck converter or boost converter or buck boost converter, they have given the LC values there. So now substitute all according to your requirements, substitute the values here, you will get the L and C value, you can just design your own buck boost converters. So what are the values required here? What is your load you require? Okay, the duty cycle, you know, duty cycle you will be varying from 0 to 1. So you can just have it, but you will not go to maximum 1. Okay, so 0.9 or something. So accordingly, you can fix the value and do it. That is what is the maximum value you will take. Accordingly, you can have frequency. What is the switching frequency? So in our case, when in the lab, we took 80 kilohertz. So accordingly, 80 kilowatts was put there. And one more thing is, you know, you will take a ripple current. Mainly in most of the books, they have given as such. So the ripple current value can be taken as 10%. So ripple current equation is also given in the book. So you can even substitute in that and find the value of L. Okay, so the switching frequency is required. You require the ripple current, you require the load, duty cycle, and the source voltage. So what is the input voltage? So in case of a PV, you can just fix. My voltage will be from 0 to some 20 volts. So 20 volts is your source voltage. Then you accordingly, you can fix what will be the, so you have to just put it inside this and find what is your L value and C value. Okay. And here, in case of buck converter, your output voltage, say output voltage is nothing but equal to duty cycle times your input voltage. Okay. So here what you can do is just the output voltage, you can integrate it and find it. So if you integrate it between 0 and Ts, the whole time period, and you just integrate it and do it step by step, automatically you will get output voltage is D time Vi. Or you can just go through Netmohan book. They have very beautifully told how they have found is the voltage across the inductance they have found. So here the voltage across the inductor, the first case will be Vs minus the output voltage. The load voltage you can say, or here the capacitor voltage. That will be the VL value. This is the inductor value. Okay, so this VL is the load voltage I have said. This is the load. Okay, this is not inductor, this is the load voltage. And here in this negative, this is during the positive half cycle. You just draw the KVL, you can get it like say this is Vs. So you just write plus Vs minus VL minus Vc is equal to 0. Okay, so you can have this V load as Vc also, because load voltage will be equal to this capacitor voltage. So this is the thing. And when it is off, it freewheels through this diode. Okay, off condition. So this is the off condition. What will be the this voltage? So this is plus and this is minus here. So V minus VL minus Vc is equal to 0. So VL is equal to minus Vc. Is it? VL is equal to minus Vc. So now what you can do, this one, this is the energy stored by the inductor during this period, and this is the energy released. So energy stored is equal to energy released. Just write the equation and solve it. You will get this output voltage is equal to D times Vi in case of a buck converter. Okay, in buck converters. So just imagine that my input voltage is 20 volts. And I have kept my duty cycle as 0.5. What will be my input? I'm very sorry. I am just let me keep my input voltage, source voltage as 20 volts. Okay, and my duty cycle as 0.5. So what will be my output voltage? 10 volts. Okay, you understood? It's reduced by half. Okay, so if I keep it as 0.25, 1/4 it will reduce. Okay, so you understood. This is bucking. We are just reducing the voltage. So when you change the duty cycle, automatically your voltage is changing here. This is in case of buck. So same way in case of boost, if you see the output voltage will be equal to output voltage is 1 divided by 1 minus D into source voltage or the input voltage. Okay. So this is in case of a boost converter. Okay, boost converter. So that's why we say in boost converter it is not a linear characteristic. It is little difficult for a MPPT. So mainly if you see students, they don't go for boost or buck boost. The problem is there is a non-linearity. So little difficult. You have to be very careful about the change in duty cycle. So here in case of a buck boost converter, so many times as we already discussed in the morning, irradiation is not constant, it goes on changing. In that case, it is D divided by 1 minus D into VI. Okay, so you can just go through the Net Mohan book, all those things with this way. So in this case, how will the current change? The current also they have discussed two things. The inductor current goes on increasing. After reaching this point, when it is turned off, the switch is turned off, it decreases. And again it increases. So this is said to be continuous conduction mode. Okay, in continuous conduction mode, the current will not become zero. But there is one more thing where the inductor current becomes zero. Say, it depends on the inductor value. Say it is increasing and here it has become zero. Okay, and after that again it increases. After that, it again increases when you switch on. So this is said to be discontinuous conduction mode. In that case, when you see the duty cycle, it is little different. It is not so simple like this. In that case, duty cycle, I think it is nothing but V naught divided by some I naught, like load current and the maximum load current also it will depend. Just go and see the equation in Net Mohan book, because I don't remember much, but it is a complicated, still little more big complicated duty cycle. Okay, when your inductor value is such that it is discontinuous. Okay, so mostly when you do research with continuous itself, you find the L and C value and you will go forward. So with the same way, by substituting all the values here in our experimentation, when we did it, what we did is we had a switching frequency of 80 kilohertz. Our input voltage was 20. Our load resistance was 90 ohms. Duty cycle was a varying one. It was varying from around 0.4 to 0.9 we kept. And then we found the capacitor value and inductor value. So here you can see this is the inductor value. This is the capacitor value we got. But the main challenge, the input capacitor and in output capacitor, we get the same value, and that also we found it from there in the calculation. But the main challenge which we faced is all these inductor and capacitor, when it was real time, when we got the buck converter, they have some ESR, that is an effective series resistance is there. So this resistance value you have to find, otherwise your simulation and your hardware will not give you. How your hardware will perform, you will not be able to see in simulation. Okay, so for that again data sheet was referred. We got to the manufacturers, we talked with them, we said please give the ESR value, or you have different other techniques also to measure this resistance which is there internal present in the capacitor. So if you take a capacitor also, it has an internal resistance, that value. Similarly, if you take an inductor, that resistance. So these resistance were got from the manufacturers. We wanted the ESR value, we asked the manufacturers and we got this values. Then only you will get a perfect buck converter. We can simulate it. Say we got, like we gave it to a particular company, we gave all the values and we told them to make a buck converter and give us. So we got the buck converter, but they had put some capacitor value. Now what is the ESR? Then again we told them to measure and give us, and they measured it. And they said it will be even present in the data sheet. So you can get those values. Okay, so like this you have found all the values. Now I'll just show you the MATLAB simulation. We'll just go and see the MATLAB simulation. So first I'll just show you the buck converter model we did. First of all, as I told you, all the SR values, inductor, capacitor, everything we put. And first first thing what we did was to simulate a buck converter. We gave a constant 20 volts and we saw that when we are changing the duty cycle, what is the output we are getting. That was the first step. After that, the DC voltage we removed and we put a PV panel there. Okay, and now in MATLAB 2015 onwards, this PV model is also available. Before 2015, this is not available, but after 2015, the model PV is available. But there is once again one more challenge is, so the PV panel what you are using in your institute, that model will not be there. You require the same characteristics of that. So I'll just tell you how to change the parameters and get your parameters. Because here also we had Vikram solar panel that was not available there. So we made our own Vikram solar panel. We took the data sheet, we took all the values and we substituted it and we got it. So that I'll just show you in MATLAB how to get it. So here you can see the, oh God. I'll just change the view 1 second. I'll zoom it in. So there the P, that is not clear. That's what I just thought of increasing it. Still it is not clear, is it? What is the reason? It's not coming little clear. Any reason? Let me enlarge and show you 1 second. Now it is little clear, is it? So I'll just show you like this because it is, I'll just from one end I'll explain because some problem is there. So here DC voltage you can see I gave 12 volts. Then after that both the ends I saw at the input end and output end both the place we put a capacitor. But I told you with that even the ESR has to be put, that is effective series resistance. So that value was measured and that was put. We had a like ammeter and voltmeter just for measuring purpose. Okay, here you have the switch. So I already told you in a buck converter, a switch is there, an inductor and a diode. So that is the three circuits you can see. For switch, we gave a PWM. Duty cycle is 0.25. In the lower circuit, like other circuit also, I have just given 0.5, 0.75. So different, same circuit with different duty cycles we have tried. And at the load end also, one more capacitor we have put. So that is a low, this both the things together. Here the 80 ohm and L1 millihenry is inductor, and this 30 milliohm and 100 microfarad was the low pass filter. Okay, this was the low pass filter, and then you have the load here. So we have here at 10 ohm load, which are 9 ohms, I think 9 ohms ka load. So and we will be seeing the output that I'll just minimize and then. So this output just we are seeing in this scope here. Okay, so this is the thing. I'm just running the simulation. So it's a very simple circuit. It's compiling and I'll just show you the output. So first of all, we did the simulation in order to see the parameters, and I'm not running it fully just to simply show you. So here I did the same thing with duty cycle 0.5 point. So I think now you can see this. So I'll just change the color so that it will be a little more visible. So I think little visible. So this is the 20 volts input what we gave, and according to say 0.5, 10 volts, and it is 0.75, it is around 15 volts and 5 volts for when it is 0.25. Okay, so it is not perfectly, it is matching. So you have to again work on the ESR. Like ESR is not perfect, then you will not get a perfect thing. So inductance, capacitance value, if you measured properly and if you put, automatically you can see the different values. So buck converter was almost designed. Now what we require the PV. And after designing the PV, we require the algorithms, the P and O algorithm or different algorithms. So next we will just go into that circuit. So this is clear. I think buck converter have we designed. So next we will go on to the other model. So you can see here, okay. So the buck converter which I showed you, it's the same buck converter. I think you can get the thing. You have the inductor, like a capacitor. You have this. You have the capacitor here, this switch here, this inductor, this diode, and similarly this side also the capacitor and inductor. You have this DC, the PWM generator. Okay, so now this is coming from the P and O algorithm. Before it was simply I tested whether my buck converter is operating properly or not. Now this is coming from my buck converter. Sorry, this is coming from my PWM. Okay. So now this is my PV. You can see here the, one second. So this is my PV. Okay. It's not enlarging there. अभी हो रहे हैं बट मुझे दूसरा फॉर्म है तो वहां ही काम कर सकते हैं वो ऐसे एनलॉज नहीं हो रहा है ओके सो हियर यू कैन सी द पीवी हियर this I can't show my cursor, that's a problem. So the PV is here. So this one which I put as an aeroplane, actually this is the PV. I just showed the people how to mask it, so I'll just show you people also how to put your own picture and all. So this is the PV. This is your perturb and absorb algorithm. So in this place you can put your GA, you can put your PSO, you can put your artificial intelligence, you can put your incremental conductance. Just the algorithm will change there. Okay, and here to this algorithm you can see only two important parameters are going. One is the voltage of this PV and one is the current of this PV. Okay, and the duty cycle will be my output to this switch. Okay, the duty cycle is my output. Okay, so now I can just show you this PV. So this is the PV character. PV. This is my PV, and this model is already available in MATLAB. I've just taken the MATLAB model as such. Only thing, as I already told you, is the required thing is when I double click this, a window will open. And you can see here the parameters. So you can see the parameters here. You can see Vikram Solar. All the parameters are written here. Is it? This is not there in MATLAB. Vikram Solar module is not available in MATLAB. So when you actually go into MATLAB, you can see that they have different other solar panels given with different other ratings. But what we require the panel what we have it. So for that, we did masking. So this solar panel, now I told you, those who are having 2015 and above, you get this solar panel, you can just go and take it. But again, your model will not be there. You have to change it accordingly. Or you can go to MATLAB file exchange. Okay, go to Google. In Google, go to MATLAB file exchange. In MATLAB file exchange, if you go to MATLAB or Simulink environment, like coding or Simulink environment, their PV models are already existing. So from there only I took this model. So similarly, you can get your model there. In that model, you have to change according to your PV panel. So how will you do that? That I'll show you. So just right click on this model. Okay. So when you right click, you have something called mask. You have something called mask. I'm just telling it because if I zoom it, I'll not be able to again show the next step. So I'm just showing here. You right click the PV. You get a option where you go to mask. In that mask, go to edit mask. Edit mask. So just click on that edit mask. You will get a window opening there. So this is the window. Okay. So this is the window. So in this window, you can see here image IM read. So in that image IM read, you can give any image what you require. Automatically that image will come. So you have to see which location this B747 is there. It will be in the MATLAB file of C drive where you have installed your MATLAB. It will be in one particular location inside Simulink. So go and change that. Whichever picture you are putting from your own end, you just go and put your picture there in JPG form. You call it here, it will come here. But once it comes here, what you have to do is you have to refresh it. You have to shut down your system and turn on, then only the picture will come. Okay, or already existing picture, it will change accordingly. After that, what will you do? You will go to this parameter here. So when I show you, say sometimes it will not be so clear. So I'll just tell you what I'm doing. I'll go to this parameter, and then after that, I'll go to the initialization, and I'll be entering all the values of Vikram Solar inside that. So I'll just show you how it is done. So here, this B747, let me change it to Simulink theme. One Simulink theme picture is also there. So let us see that how it is changing. So here, the picture has changed. Now it's a Simulink theme picture. So you can put your own picture also. Then go into parameters. Okay, in parameters also see all these parameters are there. Okay, these parameters are already defined. No problem, because this in MATLAB when you took all the other solar panels also have the same parameter. No problem. Now next go to initialization. So in initialization, this is very important. Okay, this initialization, what we actually did is this type 1 was some other solar panel what was initially there. So what I did, I took the Vikram solar panel data sheet and I took all these datas. This one, how many parallel series cells are there? What is the VMPP, PMPP, IMPP, open circuit voltage, short circuit current? All these parameters are there in the data sheet. So take all these parameters and put it in the initialization. Delete one of their type 1. Okay, type 1 was some other solar panel. I put my own solar panel with all these things and edit. You're doing what you're doing. You're editing the mask. Okay, and now you just apply changes and come out. You will get a solar panel like this with your characteristics. You can draw the PV characteristics, VI characteristics. You will get the same characteristics of your solar panel. You understood this? So where will you go for this? Go to MATLAB file exchange and go to MATLAB file exchange in that Simulink environment, and there just go and search for solar PV model. So automatically you will get this model, or you can go to MATLAB 15 environment and you can get it. Next is how did we write this perturb and observe? So you can go to this library. In this library you have, so you can see here, in library Simulink environment, you have something called the user defined function. Okay, so I'll just click on this and I will take a MATLAB block from that. So here I'm just clicking on this and I am taking this MATLAB function block into my environment. Okay, so this block is this block. And after that, what I did, I'll be just writing the whole program. So this whole program, if you see, what I'll do, I'll be just taking I'm just giving input as voltage, current, and 2 other inputs, parameter and enable. So 4 inputs will come and I have 1 output. Duty cycle is my output to this block. And again, same thing, you have to just acquire it. So you can see here, I'll be acquiring, I'll be acquiring the value, I'll be finding the power, I'll be changing my change in power also. And with that change in power, I just compare whether that power value is less than or equal to. Accordingly, I'll be changing my duty cycle. So the algorithm, what I told you there, the same algorithm. If it is incremental conductance, you just find the conductance and do it. It's just if then rules, and you have to use it as we do it in C programming. Okay, so this whole algorithm is written inside this. So I'll just show you a simple example taking this. I'm just double clicking on this window. So you will have a function like this. Okay, this function is coming. Now I'm going to write the program. After writing the program, the centers will be able to see it clearly. Okay, and now it will not be much clear. Once again, I'll be repeating for the center, for the nodal centers. So I have two inputs here. Let me keep Y1 and Y2 are my outputs. I have two outputs, so I am just entering two outputs here. Okay. Okay. So next, I have two inputs. Let me keep it as U1 and U2 are my two inputs, and I have to define my input and output. So let me keep my Y1 is equal to U1 into some 100. Simply, this is just to show you I am just giving my Y1, and my Y2 is equal to U2 into some 1000. I'm just defining these two. So for the centers, I'll just show you what I've written here. So here you can see I have defined two input outputs. Okay, in our case, only one duty cycle is required, but I'm just telling you how to write a function. Okay, in MATLAB, just put that embedded block, and after that, go inside that. You have two outputs, Y1 and Y2. You have U1 and U2 are my two inputs. Okay, so here voltage and current as I can give it as input, and my duty cycle is output. And I have to define what is my output. First output is I have written U1 into 100. My second output is nothing but U2 into 1000. Simply, this is for simple thing I have done. And just close this window. So automatically you can see here my this have changed into this format. Now it has two inputs and two outputs. Now connected to your system. Okay, so if it is a duty cycle, I'll be connecting it to my PWM generator. My voltage and current I'll be connecting here. Inside, write down the program, whichever program you want. Okay, these perturb and absorb incremental also in MATLAB file exchange, it is already available. So you need not go and write it, you can just take it, because these are the conventional methods. Whenever you want to test your algorithm and you want to prove that it is better than your conventional, you need not rewrite, you can take those algorithms and keep it here. Okay, is it clear? So now this is the model, I'm just deleting this, I don't want it. So let me run and see what output I am getting. So what I'm seeing is at the input and solar end, my output also should track that maximum point. Okay, and this is my irradiation, sunlight. So this sunlight I've just changed. First it was 1000 watts per meter squared. After that suddenly I changed into 250 watts per meter squared. Again I increased to 1000. So I'm just changing the irradiation because irradiation will not be constant always. So I'm just running the simulation. So I understood all of you understood how I did the simulation. So very simple thing. I'm just running the simulation. It's already across 4, so people are just looking at the clock. I'll leave the centers also with this simulation. Then we'll continue in the next class because this topic is a very big. I have to show you how to connect to hardware and all those things. So next class also we'll just continue. So now I've just run the simulation. Let me see the Simulink output. Okay, so this is the output what I'm getting. So we can see here 2 lines. So my output is almost trying to track my input. And this is not the irradiation. This is actually the voltage. Okay, this is the voltage. So initially it was around 17 volts. Then it dropped to, when the irradiation changed, the voltage also dropped. So my output is also trying to track the maximum according to perturb and absorb. Okay, it is trying to catch my thing. So this is not the power also. This is power curve is this. So this is my power curve. I think all of you can see this curve properly. Okay, I'm not changing the color. You can just see it here. Same way, this is power. So power. So the power curve you can see around 34 or 33 or something. It's coming here. Okay, so it should be around 37. So in the sense, initially it's going till 37, but it is reducing. Still, it is not going. If your PV is tracking that 37, it is a perfect method. That is why I'm saying P&O is also not so perfect. You can go for artificial intelligence, then suddenly, but the thing is it is tracking. See, you can see that it is tracking almost when the radiation is changing, it is trying to track the power. Voltage also I showed you. So similarly, the other methods also you can work on. Okay, so tomorrow I'll be just showing you, this is not over, actually how to implement this with hardware. So we'll just see this. simulation. So you will just see that how to implement in hardware also. We will just see this thing tomorrow. Okay. So today, if you have any doubts till this, you can ask. Tomorrow morning also I have an after I'll just see. I'll be taking you the multi-level inverters also in case time now permits. I'll just put it in other class and I'll be finishing you. And just if you are interested, I can just show you how to track maximum power using artificial intelligence like ANFUZ, adaptive neurofuzzy also. It is better than I can show you that also, because how to get data from this, how to train a network, and how to, yeah, in artificial intelligence, if you are interested, I didn't put it in this course also, but if you are interested, I can just show you that. That's also very simple. How to acquire in Arduino, I'll just show you in hardware, because when you want to do it with hardware, you can do it at your end itself. At your home also, you can do it. So very simple hardwares are there that I'll be showing you, and tomorrow we'll do that. And in case artificial intelligence, I get time, I'll show you that also. How to get data from this, how to train a network, and how to make a model and come and connect it here. Okay, so that also we can see.